Hello, my name is Eriguchi. Today, I talk about d-multiplicative secret sharing for multipartite adversary structures. This is a joint work with Noboru Kunihiro. First, I briefly explain secret sharing. In a secret sharing scheme, uh, some secret information S is divided into several shares, and each share is distributed to one player. And we assume an adversary can corrupt a subset of players, and we define an adversary structure delta as a family of such subsets the adversary can corrupt. And we call a subset of players forbidden if they have no information on the secret. So if any subset in delta is forbidden in this secret sharing scheme, the adversary cannot obtain any information on the secret. So more formally, we let P be the set of n players, and we define an adversary structure on P as a monotone decreasing family. And we assume that the domain of secrets is a finite field of size Q, and we let Si be the set of the ith possible shares. Then a secret sharing scheme is a randomized function whose input is a field element and output is a table of n shares. Then we call the secret sharing scheme delta private if no information about the secret leaks out from a subset in delta. And we measure the efficiency of the secret sharing scheme by the total information ratio, which is defined by the ratio between the total size of n shares and the size of a secret. So it is important to minimize the information ratio to achieve better efficiency. Next, in this work, we study a special class of secret sharing schemes called d-multiplicative secret sharing. So I first provide a definition. A secret sharing scheme is called d-multiplicative if there is a deterministic function mult for each player I. This function takes d shares as inputs, and if each share corresponds to the ith share of the secret Sj, then this function generates an additive sharing of the product of these secrets. So in other words, the players can locally compute the additive sharing of the product from their own shares. D-multiplicative secret sharing can be used to construct unconditionally secure multiparty computation protocols for computing multivariate polynomials of total degree at most d. So I show a simple protocol for computing the product of d secret inputs. So first, each client shares their secret inputs among n servers, and by the multiplicative secret sharing, and each server can locally compute the function mult and obtain the additive sharing of the product. Then an output client collects these additive sharing and reconstructs the desired output. Then the communication complexity of this protocol is proportional to the information ratio of the underlying secret sharing and the bit length of the field size, Q. And this protocol is passively secure against an adversary who can corrupt a subset of servers in delta. So it is important to construct d-multiplicative secret sharing schemes such that the information ratio and the field size are small, and it is delta private for a large adversary structure. Next, I briefly show the previously known results about d-multiplicative secret sharing. First, as a negative result, delta private and d-multiplicative secret sharing exists only if the adversary structure is of type QD. So that is, no d subsets in delta can cover the whole set P. So in other words, it is impossible to construct d-multiplicative secret sharing schemes for adversary structures which are not of type QD. So, and on the other hand, for any adversary structure of type QD, there is d-multiplicative schemes, but the information ratio is exponentially in n. Yeah, so this is very, very inefficient. And when d is equal to 2, any linear secret sharing scheme realizing the adversary structure delta can be converted into the 2-multiplicative one with small overhead. And so this is more efficient than the generic construction. And Shamir's scheme is also a d-multiplicative, but this scheme is private only for threshold adversary structures. And these schemes achieve the optimal information ratio. And finally, to reduce the field size of Shamir's scheme, d-multiplicative schemes based on algebraic curves were devised. So if we choose an algebraic curve with many rational points, then we can construct d-multiplicative schemes over smaller field than the Shamir scheme. But this scheme requires a bit more players in the protocol. Next, I explain our proposed secret sharing schemes. Our scheme can deal with multipartite adversary structures. So I first described the definition. Let pi be a partition of P. So we suppose that P is divided into L parts, P1 to PL. And we call a permutation on P a pi permutation if it maps every player in each part to the same part. And then an adversary structure is called pipartite if the image of every subset in delta by any pi permutation is also in delta. So informally, in a pipartite adversary structure, whether a subset X is in delta or not is uniquely determined by the associated vector defined like this. So, for example, threshold adversary structures are one-partite with respect to this trivial partition. And in addition, every adversary structure can be viewed as an n-partite adversary structure with respect to this partition. And now, in this work, we propose two kinds of d-multiplicative secret sharing schemes for L-partite adversary structures. The first scheme can be applied to any L-partite adversary structure of type QD because there are d-multiplicative schemes only for QD adversary structures. So our scheme can deal with all the possible L-partite adversary structures. And this scheme achieves polynomial information ratio, so if L is constant. So this scheme is much more efficient than the generic construction. And specifically, the information ratio is up-bounded by the size of this set of vectors, which consists of all the maximal vectors with respect to the coordinated order. So next, the second scheme is applicable to a smaller class of L-parted adversary structures. Specifically, let P be the vector defined like this, and C be the convex hull of the set of vectors. So delta has to satisfy this geometric condition, which is a stronger assumption than type QD. But this scheme achieves better information ratio than the first scheme if epsilon is not very small or constant, for example. Now I explain the detail of our proposed schemes. But due to the time constraint, we only explain our first scheme. Our first scheme is essentially a combination of Shamir's threshold schemes. So I first describe the Shamir threshold scheme. Assume that the field size is greater than n, and fix n distinct non-zero elements of FQ, alpha 1 to alpha n. So to share a secret S, we first randomly choose a polynomial f such that the value at 0 is equal to s, and the degree is at most t. And we give the player I the value at alpha I. Then any subset of size at most t is forbidden in this threshold scheme. And this scheme is known to be d-multiplicative if dt is less than n. So now I consider any L-partite adversary structure of type QD, and let pi be a partition of P, and we list all the maximal vectors a1 to an, and in the following, v of j mean the jth entry of a vector v. And first, I characterize L-partite adversary structures of type QD. Specifically, bipartite adversary structure is of type QD exactly when any d vectors do not exceed this vector with respect to the coordinated order. So this means that there is an index j such that the sum of these entries is less than the size of pj. So in particular, for any combination of d maximal vectors, we can fix an index psi I such that the sum of these entries is less than the size of the corresponding part. So we will use this lemma later. Now, assume that, as in Shamir's scheme, the field size is greater than n, and fix n distinct non-zero elements of FQ. So first, to share a secret S, we randomly split S into n field elements S1 to Sn, and next, for each I and j, we choose a random polynomial Fij such that the value at 0 is equal to Si, and the degree is at most Ai of j. So in other words, for each I and j, we independently run Shamir's scheme with secret Si and threshold Ai of j, and distributes the shares into the players in Pj. So each player receives one share of Shamir's scheme for each Si, so he receives n field elements totally. Now I prove that our scheme is delta private. Let A be any subset in delta. Then the associated vector is upper bounded by some maximal vectors AI. And then the players in the jth part have only at most AI of j shares of the corresponding Shamir scheme. So the number of shares does not exceed the threshold, so they have no information on SI. So because we independently run these L Shamir scheme, so the players in A have no information on SI either. So therefore, they have no information on the secret because it is masked by the by SI. So this proves the privacy of our scheme. And next, I prove that our scheme is d-multiplicative. So consider any d secrets S1 to SD. So player K receives n field elements for each secret. From the construction, this S to M is first divided into n field elements, and each Si to M is shared via some polynomial. Then the product of these secrets it can be written as the sum of n to d monomials, and each monomial is the value of this polynomial at 0. And here we set j as psi I. From the definition of psi, it holds that the sum of these values is less than the size of pj. So the degree of this polynomial is at most this value. So the degree is less than the size of pj. So therefore, the players in pj can compute this value from their shares by Lagrange interpolation. So finally, we change the order of summation, and we set this value as the output of the function mode. We note that this value can be computed only from the shares of the player K. So this proves the multiplicativity of our scheme. Finally, I show an example. Suppose that d is equal to 2 and n is even. And let S be a subset of size n-1. And we consider the following bipartite adversary structure, which contains all the subsets of size at most k-1 and all the subsets in S of size k. So then the maximal vectors are these two vectors. So therefore we can construct two multiplicative secret sharing schemes whose information ratio is equal to 2. More concretely, we show the shares of the players as follows. So for a secret S, we first divide it into the S1 and S2, and S1 is shared among the players in S via a polynomial of size at most k, and the player N receives S1. And S2 is shared among S via a polynomial of degree at most k-2, and player N receives the value of degree 1 polynomial. Now I prove that the two-multiplicativity of the scheme. So let S and T be two secrets. Then the players receive the following shares. So we use F to denote the polynomials corresponding to S, and we use G to denote the polynomials corresponding to T. So the product of the two secrets can be written as the sum of four monomials. The first monomial is computed by player N because he has S1 and T1. And the last three monomials can be computed by the players in S because these polynomials are of degree at most 2k minus 2, which is less than the size of S. So they can compute these values by Lagrange interpolation. Finally, we summarize this presentation. In this work, we propose two kinds of d-multiplicative secret sharing schemes for L-partite adversary structures. The first scheme can be applied to any L-partite adversary structure of type QD, and the information ratio is polynomial if L is constant. So this is much more efficient than the generic construction. And the second scheme is applied to L-partite adversary structures satisfying this geometric condition, but it achieves better information ratio than the first scheme if epsilon is not very small. So our future work is so both of our schemes are essentially based on Shamir's scheme. So the field size must satisfy the field size must be sufficiently large. So future work is a construction of the multiplicative schemes of a smaller field. So this can reduce the communication complexity in the protocol. And in addition, the verifiability of d-multiplicative schemes is considered in this paper. So verifiable d-multiplicative secret sharing can detect malicious behavior in the protocol. So it will be important to extend our proposed scheme to the verifiable schemes. So they are references of this work. That's all. Thank you.